Welcome to Daily Papers. Imagine you have a brilliant detective. They can solve any case, connect any dots, and reason their way out of any puzzle. But there's a catch. This detective implicitly trusts one single source for all their clues, a source that can be secretly edited by anyone.
That detective is going to have a very bad time. And it turns out, so are our most advanced AI agents. A new paper titled Oracle Poisoning, Corrupting Knowledge Graphs to Weaponize AI Agent Reasoning shows just how easy it is to trick an AI, not by breaking its logic, but by poisoning its source of truth.
This isn't the kind of AI attack we usually hear about, like prompt injection, where you're trying to trick the AI into ignoring its instructions. This is something sneakier. The paper defines a new class of attack they call Oracle poisoning. The AI's instructions are fine, its reasoning is perfect, but the data it's reasoning from is a lie.
The authors use a fantastic analogy to explain this: Plato's cave. Imagine the AI agent is a prisoner chained up in a cave, forced to look at a wall. The only reality it knows is the shadows cast on that wall. In this case, the wall is something called a knowledge graph.
Let's break that down. What's a knowledge graph? For an AI that works with software, it's like a giant, hyper-detailed map of a company's entire codebase. It shows how every piece of code connects, what functions call other functions, what depends on what. It's a massive, structured database of facts. The AI treats this map as an oracle, a trusted source of absolute truth.
Exactly. The shadows on the wall are the answers the AI gets when it queries this knowledge graph. So, what happens if an attacker can sneak into the cave and corrupt the wall itself? They can change what shapes are casting the shadows. The AI, reasoning perfectly based on the new shadows, will come to completely wrong conclusions.
And that's precisely what the researchers did. They tested this on a real production-scale system with a knowledge graph of 42 million, that's million with an M, nodes. They ran several attack scenarios, but one is particularly chilling. It's called call graph security evasion.
It sounds scary, and it is. In this attack, they looked at a piece of code that was vulnerable to something like an SQL injection attack, a common security flaw. Then, in the knowledge graph, they just invented a fix. They added a fake function called validate and sanitize input, and drew lines on the map to make it look like this fake function was protecting the vulnerable code.
So the sanitizer function doesn't exist in the actual code at all. It's just a ghost in the machine?
A ghost in the knowledge graph, exactly. So when a developer asks the AI, hey, is this code secure? Check for input sanitization. The AI consults its trusted map. It sees the fake function, follows the lines, and reports back with full confidence. Yes, SQL injection appears to be mitigated.
Wow. Okay, so how well did this actually work? Did any of the AIs see through it?
This is the headline finding of the paper. They tested 9 different large language models from OpenAI, Anthropic, and Google. Under realistic conditions, with a reasonably competent attacker, every single model was fooled. The success rate wasn't 80% or 90%, it was 100%.
100% across all major models. That's unambiguous.
Completely. Out of 269 valid trials, all 269 accepted the fabricated security claims. The paper points out that the attacker doesn't need to be a super genius. A naive attacker who uses suspicious names like Hack Sanitize V2 gets caught. But an attacker who uses plausible, professional-sounding names succeeds every time. It reframes the question from whether a model can be deceived to how much effort an attacker needs to invest.
A really fascinating finding was about how the AI receives the information. They found that if they just gave the fake data to one of the AI models as plain text in a chat message, the AI was actually skeptical. It had a 0% trust rate.
Right, but that exact same data was delivered through the AI's official tool for querying the knowledge graph. Its trust rate jumped to 100%. This shows that AI agents are being built with an inherent trust boundary violation. They treat information from their tools as ground truth, not as a claim to be verified. The channel matters as much as the content.
So if this is such a fundamental problem, what can we do about it? Are there any defenses?
Thankfully, yes. The researchers tested a few things. First, the things that don't work. Just telling the AI and its system prompt, "Hey, be careful and verify your sources," had basically zero effect. The AI would say, "Okay, I will," and then proceed to trust the poisoned data anyway.
Classic. So what does work?
The most straightforward defense is simple access control. Just make the knowledge graph read-only for the AI agent. If it can't write to the database, it can't be used to poison it directly. This eliminates the attack vector entirely.
Okay, that makes sense. A simple, strong lock on the door. What about more advanced solutions?
The other really effective defense was multi-tool cross-verification. Basically, you don't just give the AI one tool. You give the knowledge graph tool, but you also give it a tool that can read the raw source code.
Ah, so you give the detective a second source to check against.
Exactly. So when the knowledge graph says the sanitizer function is right here, the AI can then use its other tool to check the actual source code. When it finds the function isn't there, it spots the contradiction. In their tests, this collapsed the AI's blind trust from 100% down to 0 to 25%.
So the big takeaway here is that we can't just build smarter AIs. We have to build smarter systems around them. This isn't a flaw in the AI's reasoning, but a flaw in the architecture of trust we've created.
That's the core of it. We're building these incredibly powerful reasoning engines, but feeding them information on a silver platter and telling them to trust it implicitly. This paper shows that the wall in Plato's Pave is a critical vulnerability. We need to give our AI agents the ability to turn around, look at the source of the shadows, and verify things for themselves.